Hello everyone. So previously we had discussed on the topic Pollard's RHO factorization algorithm. Yeah. So today we'll be discussing on the topic fast Fourier transform algorithm. Yeah. So let's get into the definition part. Let's see what the fast Fourier transform algorithm states here. Right. See here, the fast Fourier transform FFT is an efficient algorithm to compute the discrete Fourier transform, nothing but the DFT, to compute the discrete Fourier transform, nothing but DFT, and its inverse. It converts the signal from its domain. What it does, it converts the signal from its domain to the frequency domain, allowing us to analyze frequency components quickly. Yep. Let's get into the explanation part, man. Just listen to this carefully. So whatever we discuss here, the exact same thing will be articulating in the form of code, right? So let's imagine we have a sound wave actually. Let's imagine we have a sound wave or any signal that is represented as a list of sample points. Right? So the FFT or the fast Fourier transform here, it helps us find how much of each frequency is present in that particular signal. Yeah, how much of each frequency is present in that signal, like separating a musical chord into individual notes. Yeah, so this is one of the things. So the naive DFT algorithm, yeah, the straightforward DFT algorithm has a time complexity of big of n square. Yeah, has a time complexity of big of n square. But FFT, also known as fast Fourier transform, reduces it to big of n log n. Reduces it to big of n log n by exploiting symmetry and periodicity in complex roots of the unity. Right. So all it does is here, FFT reduces this one to big of n log n. So this is naive algorithm, right? Or the straightforward DFT algorithm. Basically, it has the time complexity of big of n square brute force. Basically, FFT, what it does, it reduces it to big of n log n by exploiting symmetry and periodicity in complex roots of unity. So that's what. Let's see the same. So the most before writing the code, I found this one also very important. Let's discuss this one. The most commonly used FFT method is Cooley-Tukey algorithm. Yeah, so we call this one Cooley-Tukey algorithm. Yeah, which recursively breaks down the problem into smaller subproblems. Yep. So let's do one thing. Let's quickly write the code. Actually, let's start writing the algorithm. Yeah. So first, I'll just import the CMath for handling the complex numbers. Right. So I'll just go with import here CMath. Yep. Next, what I'll do, let me go with a function name here, FFT, fast Fourier transform, right? So let me pass the this one parameter a here. This is fine. I'll just send this one to the variable n, length of the a. This is fine. Next, what shall I do? I'll just go with a base case. What's the base case here? So if the list has only one element, then we have to return that particular list, right? If it is having only one element, meaning if n is equal to 1, then directly we can just return the a. Yep, so this is fine. So this is the base case. Next, what we will do, we will split array into even and odd indexed elements. So I'll just make use of even and odd variables here. Even, let me assign this one to the FFT. So we will go with a recursion here, right? So we'll recursively do it actually. I'll just go with a from 0. Let me, let's go until 2. Yep. So for odd, let me assign this one to the FFT of a of same thing, but 1, 2 actually. Yep. So this is fine, I believe. Now let's do one thing. Let's initialize the list to the store. Basically, let's initialize the list to store the FFT results, right? So I'll just go with the result variable res here. This is fine. 0 into n. Next step, let's compute the twiddle factors and combine the results. We have to compute the twiddle factors here. So let's go with a for loop here. So for k in range, the range would be n by 2, right? So I'll just go with n by 2 here. So this is fine. The next step within the for loop is let me assign t to CMath here dot xp. This is fine. Let's 2j into CMath here. So this is also fine. Dot pi into k by n. So into, so I'll just go with into odd of k. So this is also fine. So this will be e to the power of minus 25 ik by n actually. Yep. So let's do one thing. Now let's combine for even half as well as let's combine for the odd half, right? So for the even half, I can just write it in this way. Result of k equals even of k, this one plus, let me go with the variable t actually. Yep. So also for the odd half, so I'll just go with a k plus n by 2. This one equals E1 of k minus t actually. So this is fine. Yep. So we have successfully combined for even and odd half, right? So next we are left with only one thing. We have to return the result. I'll just go with return. Result variable we have made use of here as res actually. This is fine. Next, let's do one thing. Let's go with the input, right? Input in the sense, let's go with the signal actually. These are nothing but the list of complex or the real numbers, right? So I'll just consider here a equals 0, 1, 2, 3. So this is fine. Next, let's compose the, let's calculate the FFT. I'll just go with the result here equals FFT of input. We are going with the a variable a, right? So this is fine. Let me pass the variable a here. Finally, let's display the result. So I'll just go with the print here. And so this will be FFT output. So this is fine. FFT output. So 1 second. Yeah. Next, let's go with a for loop for individual value in the result. Result is the variable we have considered. And finally, within the for loop, let's print the individual value, right? So I'll just pass the value. Yep. So let me explain. We have discussed the same thing actually. I have explained this one step by step. Let me explain you this one algorithm basically again so that we don't forget things, right? So import CMath, what we are doing here. So we are importing the complex this one math module since for fast Fourier transform involves complex exponentials, right? So this is fine. Next one, we are going with this one function named FFT of A. So this defines the recursive FFT function, right? So we went with the recursive inside. We have already discussed this one. N equals length of A is nothing but we are just getting the number of elements in the input signal. So what is this? If N equals 1, return A, this is the base case. We know this, right? So base case for the recursion actually. A single points FFT is itself. We have discussed this one. E1, so I'm going with the E1 here equals FFT of A of this one 2, 0 to 2 actually. We are recursively computing FFT of even indexed elements, right? So just give me a second here. Yep. So for this one, what do we call? Even of FFT, we are going with a recursion, right? Here, even equals FFT of A of 0 to 2. So this one actually we are recursively computing FFT of even indexed elements. The next one is for the odd indexed element. So this is fine. Result equals 0 into n. So this is simple, man. We are just preparing an array to hold the FFT output. Yeah. So result array in simple terms. So we are just going with a loop here, for loop. So what it does, we are just iterating over half the array since FFT is symmetric. We know this. Yep. So we have already discussed this one. T equals C math of this one exp hyphen 2j. So whatever I have written. So we are just computing the twiddle factor, right? So this is for the complex this one exponential. That is the reason actually we have imported C math here, right? So this is fine. Now result of k plus this one n by 2 equals even of k minus 2. So this is nothing but we are combining the even and odd this one odd parts for the first half. So next this one actually k minus t. So this one actually this part basically we are combining the second half as well, mirror symmetry, right? So this is fine. Mm, so this is fine. Yep. Now we are just returning the result, nothing but we are returning the final FFT output list, right? So this is it for the algo. So this is nothing but the example usage, man. Yeah. Now let's do one thing. Mm, so what is the output that we need to get? We have complete understanding of the algorithm. Yep. So what is the output that we need to get here, basically, right? So let's discuss the same actually, right? So we have given here we have called the FFT function and we are passing this input, right? So finally we are printing the result here, right? 50 result, we are printing the value actually, right? So here, one thing, we have to get the output 6 plus 0j here first, for the first value, right? The second value is nothing but the minus 2 plus 2j here, this one, right? Minus 2 plus 2j. So this one. For the third one, we have to get actually minus 2 plus 0j, minus 2 plus 0j for the third one. For the fourth one, we have to get minus 2 minus 2j actually, right? So why we need to get the output? So basically the first input indicates that we are representing the DC component actually, sum of all the input values, sum of all the input values. You can just sum this one, 3 plus 2 plus 1 plus 0, 0 plus 1 plus 2 plus 3, it is 6, 6 plus 0j. Yep. The second one here, frequency component 1 actually. We are just considering the frequency component 1, showing a mix of sine and cosine parts. Yeah, sine and cosine parts actually, minus 2 plus 2j. Yep, so this is also fine. The third part here would be frequency component 2. It is purely real. It is purely real, minus 2 plus 0j. So this is also fine. What is the final one here? Frequency component 3, complex conjugate of component 1, nothing but the symmetry property. Yeah, nothing but the symmetry property, right? So these outputs, basically what it does, it represents how much of each frequency exists in the original signal 0, 1, 2, 3. Yep. So we should get these outputs. Yeah, accordingly with the input that we have given, we have to get these outputs, right? So let me delete this one. Yeah, let's try to run the code as we are done with the algorithm. Yep. So now let me give here control J. So yeah, Python followed by the file name.py. Yeah, see here 6 plus 0j. So this is fine. Minus 2 plus 2j, minus 2 plus 0j. So this one we are getting minus 19, this 198. Actually, this one it's almost equivalent to the minus 2. We had considered minus 2 minus 2j, right? So this is also fine. Not a problem, not a big deal. Yep. So now we are getting the desired output. We are getting the desired output. Yep. So we are done with the algo, right? So as we are done with the algorithm, so before moving on with the next algorithm, let me summarize whatever we have learned so far. Just try to remember these 3 to 4 points, whatever we discussed, right? So the first point here would be FFT, or the fast Fourier transform, efficiently computes the DFT of the sequence. Yeah, FFT, it computes the DFT of the sequence. Yeah, so this is fine. DFT of the sequence. Yep, so this is fine. So next, let's move on with the second one here. Second one, it reduces the time complexity from big O of n square to big O of n log n. We have already discussed this one, so this is one of the very important things. The naive or the straightforward, this one, what we call DFT algorithm. Basically, the time complexity of it is big O of n square, and this reduces, actually FFT algorithm reduces it to big O of n log n. Yep, so this is fine. So the third point here is it works by dividing the sequence. We know this, right? So it works by dividing the sequence, yep, into even and odd parts recursively and combining results using the complex roots of unity. Yep, so this is fine. The main fourth point here is the main one. The main point here is FFT is widely used in the use cases, actually signal processing. So we will be making use of, or we usually make use of this one, FFT in the signal processing, image analysis, image analysis. This is also one of the thing. And mainly, if you would have heard of FFT algorithms, usually we make use of it in the audio compression. So I have heard of this. Basically, we would be making use of this in the audio, this one compression, basically, right? So I have heard of it, that we'll be making use of it in the audio compression, right? Also, we'll be making use of it in the image analysis and the signal processing as well, right? Sorry, signal processing. Sorry, signal processing. Yeah, so these are some of the very important points that we need to remember at any cost, right? So, yep. So, okay, this is it for the algorithm, right? This is it for the fast Fourier transform algorithm. Next, we'll be discussing about the topic, or the algorithm, this one, number theoretic transform, the last one in this playlist, actually. Next, we'll be moving on with the geometry algorithm. So next algorithm is going to be the last algorithm that we'll be discussing in the number theory algorithms playlist, actually. So, yep. So as I've said, we'll be discussing on the topic, this one, number theoretic transform algorithm next. Yeah. After that, so we'll be moving on with geometry algorithms, right? So for now, this is it. Thanks for watching, guys.